the energy stored in an inductor. We know in electrical circuits, we like to look at the power. So we know for all electrical components, the power is equal to the voltage times the current. Well, the voltage across the inductor, that's L di dt, or that's the inductance times the rate that the current is changing with time. So if we multiply L di dt times I, we can also get to the power absorbed in an inductor this way. And it's absorbed if we're using passive sign convention. The energy then is stored in that magnetic field in the core of the inductor, which is a solenoid. That energy, we'll use the symbol W for that. We'll subscript L to distinguish that it's the inductor. And we can always get energy by integrating power over time. So if we want the total energy stored, we can integrate from times t is equal to infinity to the current time t. So what we'll plug in then for P is our L di dt times I. So our voltage times our current, then we can replace the voltage times the current dt with our I di dt dt. Well, here we can see that the dt's are going to cancel, and we're just integrating L I di. So, but when we're integrating over I as opposed to over t time, or over current instead of time, then we're integrating from our current being 0 at time time t is equal to negative infinity before anything happened, and then we're integrating till the current at the time t is equal to t. So we'll integrate from 0 current to our current at I at time t of I di. So now when we're integrating I di, we just have 1/2 I squared, so we end up with 1/2 L I of t squared. So that's the energy stored in our inductor. We got it through looking at the power. And it's really much easier to look at the energy in the inductor. We just need the current as opposed to the rate that the current is changing with time, which we need for the power. If we want, we can also find our energy stored in the inductor in that magnetic field by integrating with, instead of from negative infinity to t, just from our initial time t0 to t, but then we have to add back in that constant of integration. In this case, it's the energy at time t naught, or whatever that t naught time is. Usually we say an initial time is t is equal to 0, but it can be any time that we want to look at the energy stored over that time period from t naught to t. So again, we'll substitute in for our power, I di dt. We can cancel out the dt's, and then we integrate over current instead of over time. So our current at time t naught to our current at time t, I di. So we still get the 1/2 Li squared, but we have to evaluate at the limits of our integration. So we get our I of t squared minus our I of t naught squared. But when we add back in that energy at time t naught, well, that's our 1/2 L t naught squared. So the total energy, these two will cancel each other out, and we'll still end up with just 1/2 L I of t squared. But if we want the amount of energy over that time period, here in black, this gives us that amount of energy, or that change in energy stored in the inductor over that time period. So what we solved for then is that energy in an inductor at any given time t, that depends on the current through the inductor at that given time. So as long as we know the current through the inductor at that given time, then we know the energy stored in the inductor at that current time when we do 1/2 times the inductance of the inductor. If we want to know between two distinct times, then we have the 1/2 L I of t squared minus I of t naught squared. So we have to take the difference of the square of the current at the two times and then multiply that by 1/2 times the inductance. So our energy storage in the inductor in general, 0 energy at any time that the inductor current is 0. So if there's no current flowing through the inductor, there's no energy stored. When the current's not 0, whenever it's not 0, there's going to be energy stored in the inductor. Power can be delivered, however, from the inductor for part of that time cycle, and it can be recovered from the inductor later. So it's delivered to the inductor, stored in the inductor and then recovered from the inductor. The inductor is what's providing the energy. So a mathematical ideal model, no energy is lost to heat. In a real physical model, we really would have to model a resistor in series with the inductor to model the energy that's lost to heat when we're storing energy in the inductor or delivering energy from the inductor. So our inductor, it can supply or absorb power. Our relationship between voltage and current in the inductor, there we're using passive sign convention, and we say this VL is equal to L DI, and we have a subscript L there, dt. So it's absorbing power if both I and V are positive. Or if both I and V are negative, it's still absorbing power. But it's delivering power if the current is negative and the voltage is positive, or the current is positive and the voltage is negative. If we compare that to a resistor can only absorb power. So it's absorbing power when so this formula here, right? So our VR is equal to our IR times R. If the current and the voltage are both positive or both negative, it's going to be absorbing power. If we get a current that's negative and a voltage that's positive, or vice versa, and we have our passive sign convention properly set up, then we've made an error, because a resistor can never supply power like a capacitor and an inductor can. That's it for this video.